So we'll get started in like probably 15 minutes or so. Just want to let everybody on the stream know that. And yeah, we'll have Kevin Tin speaking tonight. So. AWS is the flavor of the meetup. A little bit of GCP, but that's less prevalent. I honestly think Alibaba Cloud's going to start coming out this year. Yeah. People want to take huge engagement, and that's kind of the winner. I was seeing like some distributed transaction models that they have some memory support. They came up with a very good basis in this. Interesting. Yeah. Ooh, I'm not going to check that out. Yeah, that sounds good. Yes. Hey, how's it going? But I have the fellow who goes into my company, he's like a little oh, do what? He was close to my company. Oh, yeah. It is definitely like, yeah, it's a tough fight. Yeah. Yeah, I think probably makes most sense to me. Like one of my customers was like, well, we're going to be doing things in Asia, and this is the best global region. We're just going to be very like selective about the data that we're going to put on our especially for me. Yeah. People use it. Hello. Hey, Kevin. Hi. Nice to meet you. Yeah. Nice to meet you. Is this one free? Yeah, we're live and everything.
Cool. You want to give it till, I don't know, another 10 minutes and start up, another 5 minutes and start up?
Yeah, I'd say 6:40. See what's going on.
Sounds good.
It's like this. Say go for it. Get the beer.
The beer was in the keg. They may have locked it up. I think it was locked up at 6. Be cooler if they didn't. Hello. Okay, I think we're gonna go ahead and get going. 6:40. We're good, Austin. Ready to go.
Vera was saying like maybe 6:40, 6:45.
Give it 5 more minutes.
What do you guys think? You guys want to kick it off? Yeah, I can go for it.
Yeah, sure.
I mean, the stream will be available if anybody isn't here in time. Like, the stream will be there forever. So.
Yep, absolutely. Okay. Well, firstly, thank you to Galvanize for hosting us, and secondly, thank you to everyone for coming out. I know at 6:40 on a weekday, sometimes it's easier just to go ahead and go home. So thank you for coming out. So we are the AWS Meetup Group. We're based out of Denver, Colorado, and today we're going to cover some content, not all the content. Hopefully, we can get all of your questions on. Modernizing architectures with data streaming. We're going to get into Apache Kafka, as well as some coded infrastructure we've done with Pulumi. And let's just dive into this. So firstly, my name is Kevin Tin. I am a cloud application architect and a practice lead at Worldwide Technology, a St. Louis-based company. I have a bit of experience in the industry covering .NET within the JVM, where I've done the majority of my data streaming work with Scala, also with JavaScript frameworks as well on the front end. And so from a data streaming architecture standpoint, I worked with Kafka, Kinesis, inside of Azure Event Hubs. And then also from an application architecture standpoint, like I said, AWS, Azure, and on-prem solutions. I travel incessantly, grew up in Tennessee, lived in St. Louis for quite a while, and then I currently live in Denver. So the agenda for today is to create an EKS cluster in AWS using coded infrastructure. We'll get into Pulumi and I'll show you that. We'll jump into an overview of the kind of the transition within the industry going from more of a transactional-based methodology into a data streaming methodology. We will get into using the Confluent operator to create a Kafka cluster. We'll take a look at the Kafka cluster components, look at the Confluent offerings, look at Confluent Cloud, and then finally I have a demo around an IoT use case that's built on Kafka, Kafka streams, etc. So if anyone were to want to follow along with me, there's a few prereqs. I will say I'm biased towards the Mac, so most of this can be homebrew installed, brew installed. So you'll want kube control, Helm, AWS CLI, Pulumi CLI. You'll want to set up your CLI account in AWS, Node.js, and I also use Watch throughout this presentation. And so before we really get into kind of the nuts and bolts of the presentation, a quick word on Pulumi. We use this as our infrastructure as code tool. So a lot of people would probably default to Terraform or CloudFormation. Big fan of Pulumi. It allows you to write the infrastructure in the same language that you write your software in. So it's got support from Python, TypeScript. I think the .NET C# version of it is in preview currently, if not released. I know they're working pretty feverishly on that. And so with that being the case, just to jump into that just a touch, it is currently a venture-backed startup based out of Seattle. From their website, the mission is to enable every person to be able to harness the power of the cloud. Founded in 2017. The goal is to create modern applications using coded infrastructure. If you're familiar with JavaScript, TypeScript, Python, Go, .NET, etc., you can code your infrastructure in it. You can also integrate it with your IDEs that you're used to working with, IntelliJ, VS Code, etc. And also it's very convenient because it can be placed into source control and shared with your team. And you can, as such, go ahead and create best practices and share them both internally and externally. So the first order of business is to go ahead and create an EKS cluster within Kafka. And so I have let me go ahead and jump out of the slideshow here. And so with that being the case, I have created a directory called AWS EKS Infra. And within that, so let me jump into that. From the slides. So went ahead and created a directory called AWS EKS Infra and changed directories into that. And within that, so once I did a Pulumi new and pulled it down from that URL, this is the contents that was pulled down at this point. Probably worth taking a look at that directory. And so I think the main components of this are described in the index.ts file. And so at this point, we go ahead and create a VPC. We create a cluster. We export the kube config, as well as the VPC zones that we are operating in. And so I have gone ahead and done this, as it takes about 15 minutes. And so with that being the case, if you all are familiar with Pulumi, let me go ahead and take you to the stack there. And so once spinning this up inside of Pulumi, you can go in and check out the resources that have been created. And so, as to be expected when creating a Kubernetes cluster, the amount of resources are pretty vast. And so this is an overview of the resources that have been created. And so with that being the case, if you all want to follow along and try to spin this up, it takes about 15 minutes. And so with that being the case, I'm going to go ahead and jump into some slides on the theory around data streaming. Okay, we'll just go without presentation mode here. And so a little bit of background on, well, firstly, I think worth a call out. Austin Lovelace, the founder of this meetup, has been announced as an AWS community hero. So congratulations to Austin. This is becoming, this is being announced in the next few days. We got the approval to go ahead and announce it today. As of this morning, 121 AWS heroes exist worldwide, so congratulations to Austin. Nice work, man. So to get into the nuts and bolts of data streaming, so as I think as recently as about 10 years ago, the traditional process was transactional processing, where everything was based on a command, everything was synchronous, commands were ephemeral, everything was tightly coupled, and it really didn't scale well. And so at this point, what you have is you have to have the logic within a single orchestrator to go ahead and basically understand the entire ecosystem of data, if you will. And so with this particular scenario, to create a purchase, something had to go out and query the inventory, had to go out and query the account management, query the logistics, and then go ahead and notify the user. And so this is a serial process that really doesn't scale well, and it has a lot of dependencies. And so not too awfully long ago, going into the event bus based architecture, this is a good first step. And so at this point, the event bus needs to know about the various processes that are involved. But you do get sort of a slight layer of decentralization in which the event bus deals with the communication between the processes more so than the processes dealing with each other. And so with that being the case, You get semi-persistent logic. These technologies are BizTalk, RabbitMQ, and also Azure Service Bus. This is still a pattern that exists, but it certainly is not, I think, what one would call the preferred approach. Create the system on top of the events of the world, if you will. The persistence of the events also is very is suggested. And additionally, like I said, you get the replayability that allows for an event-driven architecture, event sourcing, etc. And so in this realm, we've got Apache Kafka as well as Azure Event Hubs that really allow you to get into an event-driven architecture. And so with that being the case, start with the event. The event is the most important thing. And so as the event comes into a system of record, Kafka, for example, at that point you can go ahead and start to trigger other downstream consumers of that. And so the event being the API, you get into the ability to really start to focus on what happened, not so much what we expect to happen. And so that gets you out of the pattern of polling a database, for example. And so with that being the case, when event X has occurred, you go ahead and start to trigger computations off of that, as opposed to a command has occurred and we're going to start processing because we think this is the right interval. So this really gets you out of the batch-based kind of paradigm and into an event-driven architecture. And so with data streaming, you get the real-time updates of events. You really want to deal with immutable data, and so with that being the case, always keep the event that occurred as opposed to kind of your thinking on the event. As I mentioned earlier, event sourcing becomes possible. You can repeatedly evaluate the events and start to evolve your architecture. But really at its core, the event is the most important thing, is that is the trigger that should cause computation to occur. And so just to take a step back and look at the industries that have taken a look at data streaming and event-driven processing, I think it's worth noting here that a lot of the disruptors in their industries have taken an event-driven school of thought to processing, as opposed to batch and other inferior processing methods. Additionally, to take a look across the various markets and how they use them, we are seeing the microservice adoption being basically led by an event streaming process. Logging and alerting, I think it's worth pointing out at this point that Kafka really came out of LinkedIn, and they were trying to deal with the high volume of logging that came out of it. And so really the amount of data, just dealing with it in a batch-based process was not possible anymore. And so logging and alerting is definitely a use case that is worth noting. Order processing to go ahead and get a real-time evaluation of orders, etc. An event-driven system is definitely recommended. Analytical pipelines are being derived off of events as opposed to batch-based processing at this point. Suggestions and plant data machine learning, going down to the bottom levels of the use cases that we have outlined. Okay, so at this point, I think we have, if anyone's following along, they probably have the EKS cluster in place at this point. And so what we'd like to dive into at this point is standing up a Kafka cluster within EKS using the Confluent operator. And so in order to get into that, let's go ahead and just do it live. So at this point, I'm going to go ahead and make a directory called the Confluent Kafka operator and change directory into it. going to create a new Pulumi project using that. And I'll just take the defaults at this point. I'm going to point out at this juncture that I'm going to use West 2. West 1 does not support EKS, so that's why we're going to West 2. On the meetup page, I believe it's been posted. Confluent has provided a demo license key for everyone. So this prompt here, go ahead and paste that license key into the console. At this point, we have to, based on the Helm charts, go ahead and enable only the Confluent operator. So take the defaults at this point. So here, we're going to go ahead and enable the operator. And so also worth noting, the project, the username for the Pulumi project they used to create the EKS infrastructure, go ahead and type that in here. It pulls some configuration data from that. Cool. So at this point, we can go ahead and Pulumi up, which will go ahead and get us into the steps to deploy the configuration. So it gives you a preview of the components that are to be created. So at this point, we can do a watch on the K8s cluster and see the operator come into effect. And so now that we have the Confluent operator, the next step is to go ahead and enable Zookeeper within the K8s cluster. So if you want to do that from the command line, it looks like this. Additionally, if you want to look at the project itself, that exists out here, and there is a Pulumi dev YAML, and this should look pretty familiar. This is the configuration value. So you have the option of either going into the Pulumi dev YAML at this point to go ahead and change the values, or to do that from the command line. So I'm just going to go ahead and do that from the command line. So at this point, to go ahead and stand up the Pulumi stack in the latest configuration, Pulumi up will go ahead and get you into that. I'm going to go ahead and add this skip preview at this point, as I feel like we just want to go ahead and get stuff moving. So this won't take very long. The next step in the process is to go ahead and enable the Kafka brokers. There's certain aspects of the cluster that do not work if the brokers come online second. If there's an insufficient amount of brokers, then stuff like the Schema Registry and the command center will error out. And so at this point, we have Zookeeper 0 through 2 spinning up, pending and init on 1 and 2. So let's give this a sec. So Zookeeper deals with elections within the broker cluster. And so one of the brokers is the leader and tells the consumers which partitions exist on which brokers. And so Zookeeper deals with who is the leader in the cluster. And so I believe this is being phased out to a raft-based election leader system. But for now, Zookeeper is still very much in play. So we have the 3 Zookeeper nodes running within the K8s cluster. I'm going to go ahead and enable the Kafka brokers. And then, as always, go ahead and Pulumi up once you have made changes to the configuration. So as a part of the spin up of the Kafka brokers themselves, we are going to get some storage, we're going to get some IAM roles, there's a secret to communicate, and in general, the Kafka cluster is really starting to take form. And down here, you can see that as we have Kafka 0 coming online, this does take a couple minutes to get all 3 of the Kafka brokers online. And so with that being the case, let's go ahead and let this run for a sec. In terms of what's coming up next, we're going to go ahead, after the Kafka brokers are in place, we're going to enable Kafka Connect, which is part of the Confluent platform, the control center, which we'll get into that later. That's very, very cool. Coming from the early days of Kafka, this control center is definitely super useful. At this point, we already have Kafka enabled. KSQL will come online, and KSQL is a technology that allows you to use a kind of a SQL dialect in order to manipulate and create streams. And so at that point, when you start talking about doing ETL jobs within Kafka, I would definitely look into KSQL. The operator itself, standard K8s operator, and this is basically taking charge of the K8s cluster and ensuring the right components are in place. The replicator, we are not going to enable that today. We spun up a K8s cluster with 8 nodes, I believe, and if we got into turning on the replicator, we'd probably have to resize that to give it a couple more nodes. But just in general, to cover it, the replicator allows you to move data between different Kafka clusters. As the name indicates, replicate data from one Kafka cluster to another. Additionally, we will enable the Schema registry, and so this allows you to enforce a schema on a topic, which I would not get into Kafka and not use the Schema registry. Highly recommended. This ensures that data on your topics are to be in the expected shape. Additionally, it allows you to evolve the data on a single topic, and so you can make additive changes, for example, non-breaking changes, etc. Okay, cool. So at this point, we are still bringing up Kafka. Bear with me. So I guess in the room, what is the general, comfort with using Kafka to date? Is the room generally a user of Kafka? Do you all want to get into Kafka? Does anyone have any stories about Kafka we can maybe talk about while this broker stands itself up? Oh, say what?
That would be great.
Sure. Okay. So I can tell you stories about Kafka if you guys and gals don't want to talk about what you have going on. So one of the scenarios we used Kafka for was when a customer record came in and it indicated that change had occurred. We would then trigger the downstream processing to go and pull all of the pieces of a customer record. And so at that point, there was always a golden image of what a customer looked like. And so this was a retail customer in the agrochemical industry. And so we were kind of triggering off the event of a customer has changed, they've acquired another company, they've got a new address. And so another thing that we would do when that occurred was when they acquired a new company and we had 2 different companies in our database, we would run it through a matching and cleansing process to figure out if this customer was actually another customer, and then we would start to aggregate the data together, and we would really start to drive the completion of what it is that a customer record is. And as entities get acquired and sold, they would be jumping between higher level corporations pretty often, and so we would determine that the subcomponents of a company were being bought and sold, and therefore the contact information for a given customer needed to change. So just a quick use case that we saw out in the wild. Looks like the Kafka brokers have successfully been stood up. So let's jump into the rest of the components. And so for today's demo, I'm going to enable connect the control center. We shall enable KSQL. I do not want to enable the replicator. So that being the case, so let's jump into the live version of the config file that we have here. So at this point, I want to change the config file to enable Kafka Connect, the control center. Kafka's been enabled. We're going to enable KSQL. The operator's been enabled. Not going to enable the replicator. I'm going to go ahead and enable the Schema registry, and the Zookeeper has been enabled. So at this point, we're going to spin up the additional pods within the K8s cluster to give us more of the Confluent platform. Yeah, so at this point, we are spinning up various parts of the Confluent ecosystem, KSQL, the Schema registry, etc. So we're just bringing on additional components within the Kafka cluster to give us the full functionality that Confluent provides us. Yeah, so that's a good question. So what we have is, let me zoom in here just a touch. So one of our projects is the AWS EKS infrastructure. And so with that being the case, at this point we are tied to the AWS infrastructure. We're developing the project to deploy this out to AKS, or Azure Kubernetes Service. And so this can go to multiple clouds. That is correct. Oh, the Confluent license, that was provided to us from some of our partner management friends over at Confluent. We can post this out on the website. At this point, it is on YouTube and can be replayed in perpetuity. Probably best for us to go ahead and post this out on the meetup, but this is good for about 26 days as of right now. So this does give you access to the Confluent operator if you want to get into operating, if you want to operate the Confluent offering within Kubernetes, as well as the control center. And we'll get into the control center pretty soon. Coming from the early days of Kafka, the control center is definitely really, really valuable. Yeah, that's definitely a pretty sweet offering that our friends at Confluent provided to us, was a demo license key for the Confluent offering, the whole suite. And so with that being the case, in a very long-winded way, we're back to where we were. And so at this point, everything is running. We have the Kafka connectors, we have the control center, the brokers, we have the 2 KSQL pods. The Schema registry is up and running in 2 different pods, and 3 different pods servicing Zookeeper functionality to the Kafka cluster. And so with that being the case, let's go ahead and dive in a little further. So I've spoken a little bit about the control center. Let's go ahead and take a quick look at that. And so I will continue to get more. Interesting. Cool, little syntax error there. Anywho, so from what we're doing at this point is from within the K8s cluster, we are forwarding port 9021 to our local box. And with that being the case, we can take a quick look at the control center. Cool. So the control center really gives you the visibility into the health of a particular cluster. Multiple clusters can be added into a single control center. Here you can see we have 25 days left on that license, so do get that key. Definitely very useful. So we can take a dive into the general overview of the cluster. 3 brokers, which lines up with what we're seeing down here in the watch on kubectl get pods namespace Kafka. 43 topics. A lot of the KSQL and KStreams functionality is dependent upon internal topics, and so these start to get created just internally as different services start to spin up. 1 cluster for Kafka Connect and one cluster for KSQL. And so if we want to go ahead and dive into some more specifics around the brokers, we can certainly do that. Here, going back to the Zookeeper question and electing a leader amongst the brokers, the current broker that is the leader as per Zookeeper is broker ID 0. And just general other stats as well. And so jumping into topics, we start to see internal topics that have been created by the various services within the Confluent cloud. We do have a Connect cluster as well. KSQL is active. At this point, we just have internal consumers. We do not have a replication cluster turned on. And we can just generally get into some of the inner workings of the Kafka cluster itself. Cool. Oh, say that again? Yeah. So we have brokers 0 through 2, so 3 brokers. And so a broker takes charge of what partitions go onto the different broker nodes. And so there is a lead broker that you can go to and figure out the metadata around for partition 1 on topic blah, blah, blah. Where do I go to get that information? Because the different topics are on different brokers at any given time. And they can actually move, and that's not necessarily a good thing. It's a very bad performance implication, actually, where you can repartition and move partitions between different brokers, for example, if you bring a broker online. So this is the broker that's in control of the cluster, and you can go there and figure out which which broker has which partition, if you will. Oh yeah, that's actually a really good question. So going back to the customer example, talking about brokers and partitions, how does that apply? And so we actually partitioned our customers across we partitioned our customers across different source systems. So for example, something may have came from SAP, or something may have came from Salesforce. And so using a message key, you can force a message into a particular topic. And if you don't provide a key, a hash is created and it kind of gets randomized. And so at that point, broker 2 was basically the holder of the partition that would hold Salesforce data. And then broker 1 would be the holder of the partition that contained SAP data. And so with that being the case, the broker that was the leader would be in charge of figuring out which partitions go to which brokers, as well as dealing with the replication factor so that you have a level of confidence that your message won't get lost, etc.
Is the message key the same as the correlation ID or something different?
The question was, is the message queue the same as the correlation ID?
ID, is it the same as the correlation ID?
No. Correlation ID typically is used to, across a series of processes, you have a correlation ID to correlate a series of events that occurred. So that that would be a different thing. Yeah. Good question. So with that being the case, let's dive back in here. And so at this point, we have stood up the cluster, we have the control center, etc. And so let's take a little bit of a dive into what is Kafka. And I think some of this will be we've already hit on this, and some of this we can maybe dive a touch deeper into. And so Apache Kafka's mission is to be a highly available and performant streaming platform as a distributed log. And so that distributed log component comes into play, as we were just talking about. Various brokers have various partitions, and so the log is distributed across multiple brokers. And so in the event of a broker going down, another broker can be brought up, and so the log can be replicated back to that broker, and so at that point you have a level of high availability. Originally created at LinkedIn in 2010. It's been a top-level Apache project since 2012. Open source in 2014, and it's definitely used by some of the heavyweights in the industry. And so, sorry, say that again? Yes. Yeah, so if a broker goes down, what does that process look like? And so at that point, broker goes down, Kubernetes will bring up additional pods to ensure that it is performing its job as based on the definition of the cube. And so at that point, the log will be replicated out to the new broker. And at that point, they get the Kafka cluster in general gets back to a level of reliability. You get into some interesting, scenarios there, where if you need a high level of replication across the different brokers, the consumption of records can still occur, but the producer acknowledgement at sometimes needs to wait for the new broker to be brought back up. So you can see some performance implications from your producer side when you bring a new broker online. The consume side of it continues to just kind of spin along until you get to the end of the log of messages at that point, in which the producer has not been fully acknowledged in terms of replication. So based on the amount of replication that you require, which is a configurable property within your cluster, you can get some pretty interesting performance problems once a broker goes down. But the consumers can continue to read all messages that have been acknowledged as received up until that point. I may have gone a little deeper than your question. I hope that answered your question, Austin.
Yeah.
All right, sweet. Cool.
I have a question, sir.
Oh, yeah, please.
What happens with the node that goes down? What happens with that log?
What happens with that log? Yeah, so that log is on the file system that is attached to that node. And so if that node goes down, it's gone. And so it'll come back up in a fresh state, and then the Kafka cluster will replicate out to it. And so replication is a very core, concept of Kafka. And so you generally want an odd number of brokers, and you want 3 or 5 or 7. And so if you have like, say 2 out of a cluster of 3 have been, say 2 out of 3 goes down, then they can go ahead and replicate back to 2 and bring it back online. And so there's definitely a performance hit there. Okay. So to get into the general semantics of topics, partitions, consumers, and producers, pulled this off of the Confluent website. And so here we've got the producers on the left side. Producers are simply what they sound like. They produce messages onto topics. And once the messages go onto a topic, the brokers will distribute across the various partitions. I think to an earlier point, you can see like with T0 here, T0, partition 1, partition 3. A broker is responsible for a particular partition and not the entire topic. So this gives you a level of distribution of the messages that you can really start to parallelize, if you will. And so a consumer on the other side of it is pretty much exactly what it sounds like. A consumer pulls messages off a particular topic. And so with that being the case, once a consumer comes online, it is assigned a partition or a set of partitions. So it can round robin across 5 partitions, or it can be, if you have 5 consumers on a 5 partition topic, you have a level of, a level of sequential threadability that gives you, it gives you the best performance. And so in general, the number of consumers, it's recommended to have them equal the number of partitions on a topic. If you have 6 consumers and 5 partitions on a topic, one of the consumers will basically be sitting there waiting for work and never get it. And so matching up the number of consumers to the number of partitions is definitely a best practice.
So one question, are these brokers of the same data center? I mean, like, can you have a different data center?
Are you asking about a different data center? Yes, so you can, if you talk about different data centers and different clusters, different Kafka clusters, at that point you'd want to use something like the replicator to replicate data across the different clusters. So this is an example of a single cluster Kafka implementation.
Hey, I know there's a Kafka mirror method which replicates the data. What my question is, there are 3 brokers you mentioned.
Yeah.
Are these 3 brokers in the same data center inside a Kafka cluster, or can we have a different data center broker where it will be like Kafka mirror maker where it replicates the data and everything?
Yeah, that's a good question. So the Mirror Maker will replicate the data across various Kafka clusters, but your consumer ID is what's really, that's where you're keeping track of your offsets. And so if you, at that point, you're going to have the consumers are going to be pointed to one cluster, correct?
Yeah, that's what I'm asking for. Suggestion and recommendation, keep it one cluster in one data center. Right?
Correct.
And that's all the processing. Whenever it gets ready through Kafka mirror maker, it's just replicates.
Yeah. And so for the live stream, the question was, the recommendation is to have one cluster for a set of consumers, and then if you want to get into another data center, use something like Mirror Maker or Replicator, and that is correct. And so at that point, you do have the various consumers on the various clusters have their own offset that they're keeping track of. So if you were to have 2 data centers, a consumer would not be able to commit to the offset on the remote data center. And so to dive into the anatomy of a single topic and the partitions on that, the partitions and the offsets start at 0, and every sequential message that comes in afterwards is assigned a different offset. And so the writes occur in a sequential manner. This is the log-based file system that backs Kafka, etc. To dive into the components of the Confluent ecosystem, some of which we stood up, some of which we haven't, we have the operator, which stands in its own pod. and it monitors the rest of the Confluent cluster. And so with that being the case, KSQL can have 0 to n instances, Kafka Connect can have 0 to n instances, the brokers themselves, Zookeeper, Schema Registry, the replicator, and then the control center exists in a single instance. And so also with that being the case, with Kafka Connect, you can send data out to out into S3, etc. And the backing storage of the overall Kafka cluster based on the cloud that you're using will be EBS, GCP storage, or Azure disks. To dive into some of the elements of the Confluent platform, the replicator, we spoke about this a little bit. To replicate data between Kafka clusters, another product there is Mirror Maker that's seen predominantly in the industry. Kafka Connect is to retrieve and send data to what's called sources or sinks. And this is, I think this is one of the more valuable parts of the Confluent platform, as it allows you to, without writing code, go ahead and get data from, for example, a Postgres database, and then go ahead, any new messages that come in get dumped onto a topic, and then on the sync side of it, go ahead and dump data out to another data source. An example here would be S3. So one could use Kafka Connect to pull data from a Postgres database, put it onto a topic if one wanted to write custom logic to deal with that, or a KSQL query to go ahead and derive topics off of that. You could certainly do that, but you could also just go ahead and sync it out to an S3 bucket. So at that point, you've got any new changes coming onto a table in a Postgres database, getting put on a topic, and then being put into an S3 bucket if you wanted to use something like Athena and do, some sort of data lake based on what was previously a kind of more of a legacy data source. Let's see here. The control center, which we have already seen at this point, provides you a single pane of glass into multiple clusters to see the health of it, to see the topics. One can go ahead and add topics, etc. if they wanted to. If you were to click into a particular topic and you have the schema registry enabled, you can go ahead and set the schema on a topic. Again, highly recommend with any topic to go ahead and set a schema on it, so that way you're not getting data that you don't understand or don't expect. KSQL, it's a SQL-like interface to go ahead and derive topics from other topics, do transformations. One of the areas I would implore you to look into KSQL maybe within your own work to utilize would be to look into going away from some maybe legacy ETL software. You can do a lot of the transformation within KSQL, derive new topics, use something like Kafka Connect, dump it out to S3. So at that point, you're getting rid of some older, maybe licensed products that are taking, that are costing money, and you can do this all within your Kafka cluster using a syntax that is very similar to Transact SQL that your IT department's probably already used to. And you can really start to talk about phasing out more legacy products, if you will, and bringing everything into your Kafka cluster to really provide kind of an enterprise data platform. We're seeing a lot of traction in this, honestly. And then finally, just to round this slide out, the schema registry enforces schemas on topics. And so at this point, you are really governing what data goes on what topic. You really know what to expect, etc. This is done with a format called Avro. And so once you create an Avro schema, you can use something like Avro Hugger is an open source Scala library. Works in Java as well. And so at that point, you can start to really generate your case classes based around your schemas and get people, your developers, into kind of schema-first development as opposed to exploratory development. This really saves a lot of time and definitely cuts down on troubleshooting overhead. I think maybe it's worth diving into for a second. If you were to just expect a JSON message and then all of a sudden one of the fields disappears, your application will break. And so
case, what happened? Like, it's not confirmed to the schema registry. Right? I define a schema.
Yeah.
You're going to write it with the copy, right? The schema breaks, what will happen? The producer cannot produce the message.
Okay, so to kind of synthesize the question, when you go to produce a message on a topic that doesn't adhere to the schema, what does that look like?
Yeah.
Okay, so from the producer side, you configure the schema registry, and then the producer goes out, checks the schema registry, and won't even attempt to write to the schema, or won't attempt to write to the topic if it doesn't adhere to the schema.
Validation phase over there.
Oh, say that again?
No, the validation phase before writing into the topic.
Yeah.
That's what you're saying.
Yeah, and so with, I think the latest version is 5.4, and with 5.4, there is server-side schema registry validation where the server will kick back as well. So there's actually two different workflows around schema validation, the latest of which is server-side schema validation. So, so the earlier methodology was the producer knows about the schema registry and says, this message does not adhere, I won't attempt to send it. With maybe less elaborate producers, it's just kind of brute force trying to send stuff to a topic, and the cluster knows about the schema for that topic, it will reject it. So you've got two different levels of control there for messages that don't adhere to schemas. Yeah, of course. Yeah. Okay. So with all that being said, I feel like we've kind of we kind of dove into the weeds pretty heavily, and I want to show you a demo that we have created over at Worldwide Technology to go ahead and kind of show off some of the semantics of streaming. And so at a very high level, what we have created is an IoT simulation. And so given a particular manufacturing site, we will grab temperature and pressure data, go ahead and send that on to a topic. At that point, we have a Kafka stream application that for a given processing site grabs all of the data within a window using a K-table or a Kafka table, and grabs the averages out of that. And if the average is greater than the threshold, a message is sent out, and once that occurs, if the message is sent out, a corrective action is then produced onto a topic that the original sensor producing applications, mimicking a production manufacturing site, will grab and then turn themselves off. And so it's a pretty standard play on anomaly detection. So once the readings given a 5-second window or outside of the expected, we send a message on a topic to basically go and turn a process off. And so with that being the case, I'm going to give you the kind of the full architectural diagram here. And I was having some problems with PowerPoint, so I won't go into a full presentation mode. So the terminology we've decided to use here is an oil rig. So they produce a temperature and pressure reading, and this can go from oil rig 1 up to N+1, so any number of them. They produce onto a temperature topic. At this point, we have a K-stream application that sits there and aggregates those and determines what the average of those readings are. We put that onto an aggregation topic. If something is outside of the standard thresholds, we put that onto an anomaly topic. We then have another K-stream application that is the corrective action coordinator. And so once something is outside of our thresholds, we want to go ahead and take action on the events that were triggering alerts, if you will, and go ahead and send a message back on the action topic to the oil rigs to go ahead and shut them off. So with that being the case, I'm going to jump into terminal again. So at this point, I have a corrective action producer. That is the K-stream application that will tell a manufacturing site to turn itself off. I also have a sensor reading aggregator. This is the application that will take in a time window, a series of sensor readings and determine what the aggregate or average is. And then finally, I have a sensor reading producer, and this is a Scala app that's basically just sending out slightly randomized variables within a range, slightly randomized values within a range, out to the temperature and pressure topics. And so at this point, I'm going to go ahead and spin these up, and we can go ahead and take a look at the cube itself. Let's see here. So within each of these Scala applications, let's go ahead and dive into that. There's an index TS, which is what Gloomy uses. And this will go ahead and create an image and upload it. And then we'll go ahead and actually create the application within the Kubernetes cluster. I've had a little bit of difficulty executing these commands in parallel. So at this point, let's go ahead and spin up the corrective action producer. And so to take a look at the diagram and tie what I'm creating back to the theory is, at this point I'm standing up the corrective action producer. And so at this point, once an anomaly is detected, anything outside of the normal threshold of events that should occur from the temperature and pressure readings, the corrective action producer determines whether or not it's too far out of that threshold, and will send a message back on the action topic to go ahead and turn an oil rig off in this case. So again, we are using Pulumi to create our infrastructure, and this is simply running its course. To dive in what it is doing, we have the create and upload image, and then it's going to go ahead and create the producer itself here. We have a Kate's provider. We have some outputs that are going to come out of this, the service, the Schema Registry service host name, as well as the Kafka service host name. Cool. So let's go ahead and do the same thing with the sensor reading aggregator. And to jump back into the architecture, at this point we are standing up this middle component here. And so what it is responsible for is to take both temperature and pressure readings, and over a window of time go ahead and come up with the aggregation on what those readings are. And if it is above the threshold, go ahead and send a message out to this anomaly topic. Yes?
Could you put the prior by?
Oh, for sure.
The
there's a line between the two Kafka connectors in the center,
Yes.
but no arrow. What is that line?
Oh, to the Kafka connectors?
Yeah, between the two Kafka connectors, what is it doing?
Yeah, that's a great question. So for the stream, the question is, what are the arrows to the Kafka connectors? What does that mean? So Kafka Connect allows you to either grab data from a data source, a source is the terminology there, or send data to a data persistence layer. Sync is the terminology there. And so part of our prototype, our proof of concept, and we don't really have time to get into it today, is very easily we can send data from a topic through Kafka Connect into an S3 bucket. So that's we're doing another talk on this in about a month. The live stream will be available. And so in this particular case, the data that are coming across these topics are dumped out into an S3 bucket. And so at that point, we have them in perpetuity. We can do queries on them using something like Athena. We can use Redshift, or we can send them further into Redshift or use something like Redshift Spectrum to allow our data warehouse to get at these events if ever we wanted to go back and look at the raw events, we never lose them. And that's actually that's a good segue to a pretty core topic concept, and that is retention. And so on an individual topic, a retention period can be set. And if you're familiar with like SQS, this is pretty standard stuff. MuleSoft does it, Kafka does it. If you get into needing to keep events forever, you could set an unlimited retention period, but that's going to result in a amount of storage on an EBS volume that probably isn't cost effective. So our recommendation at that point is to go ahead and dump it out using Kafka Connect into S3, into cold storage, and bring it back when you need to audit some sort of event. For example, an oil rig had a catastrophic issue. Like, let's go back and look at that sensor data at some point in the future, but we don't need to really keep it in Kafka for right now. And so I think standard retention periods that we've seen have been somewhere between 1 day or 30 days. You can keep them in perpetuity, but you really have to start planning on the storage costs for the EBS volume at that point.
The New York Times stores all their issues in Kafka. Do you know why people do that? Why would people store all of their data in Kafka?
Oh yeah, that's a good question. So the question was, the New York Times stores all of their data in Kafka. Why would someone want to do that? And so they're probably doing something around a concept called K-table, which is a way to aggregate things and keep like the current state of a given entity across multiple topics at one time. And so I think there's two reasons. One, you'd want to be able to combine this data on some historical level and really have like the full picture across time. And secondly, a reason someone may want to keep all of the data on a topic forever is to do an event sourcing architecture. So if you have the raw data is basically, that's the most valuable thing. I think there's a phrase, data is the new bacon, right? And so at that point, if you have all of the data in perpetuity back to when you started to receive it, you can go back and replay that data and really start to derive new data from that. So it's one of those, like, to use a cliche, you don't know what you don't know at this point. But if you have the raw data and then you figure out a new way that you want to use it and derive it and maybe train a model, if it's there in Kafka, you can do that extremely quickly. So I think that latter would be my guess. I don't know for sure, but I think the event sourcing paradigm is probably why they keep their data in perpetuity. All right, so at this point, let's go ahead and get this third component stood up. At this point, I am standing up the stream sensor reading producer to pull this back into the diagram. This is actually the component of the architecture that is synthesizing the production of data that would represent an oil rig. And so we'll give this just a sec. Yeah, question?
The sensor, to get back to the slide, the sensor
Yep.
the last 100 events, there's an anomaly, and then sending that forward to the anomaly topic.
So the sensor producer, I think the question was, what is the sensor producer?
Sensor processor.
Oh, yeah, okay, so what is the sensor processor? Yeah, yeah, absolutely. So the sensor processor is keeping a table that's configurable. I think we're at 5 seconds in our current configuration. And so it keeps a table like it's a tumbling window, I believe, that basically has the last 5 seconds worth of data for all of the sites. And then it will then take an average across those 5 seconds, because any one event that comes in is likely to be very high and then very low, and so you need some way of kind of normalizing. And so if the average across 5 seconds worth of data for a given sensor is in a state that indicates there's a problem, then you really have to start thinking that something really is occurring that you need to maybe take action upon. And so that is the aggregation of the sensors across time.
And you're using 5 seconds as an example. It could be anything.
Yeah, it could be whatever window you want. It could be sub-second, it could be hours to days if you really wanted to. The configuration of that window will have an impact on how much storage you need, because it has to be kept in the log locally, in memory, etc. So yeah, there are some, I think, decision points there, but yeah, that is basically kind of, I think, sanitizing the sensor readings that are coming in based on our simulation in a random fashion. So yeah, that's pulling it all together and saying over the last 5 seconds, is it on average something that's an anomaly above the threshold that we expect? Yeah. Okay, cool. So at this point, let's go ahead and take a look at the pods, make sure that they are bit of a fail there. Interesting. Okay, so my issue was I went application singular, not plural. So at this point, what we have are 4 pods for the sensor reading producers. Those are the randomized, pseudo-randomized values for temperature and pressure. We have the sensor reading aggregator, which to our conversation earlier is what is going to go ahead and take the time windowing and say this is above or below the thresholds. And then also the corrective action producer. So to tie this back to something visual, I'm going to go ahead and forward a couple ports and then bring up a dashboard that we have to kind of show the state of the world in terms of the production sites that we are mimicking. Bear with me. Applications. And then one final step is to go ahead and spin up the UI for our sensor reading command center, if you will. So let me jump into that. So this is just a Vue.js application that we put together to kind of visualize the overall application ecosystem we've been talking about. So we'll go ahead and start everything up. So we have 40 different production sites. Let's jump into one that's still running. And so here we can see that 5-second window of individual data messages that are being pulled in. And so let's jump back to a production site that has been stopped. And so at this point, site number 30 was stopped as it was outside of threshold, and on average, either sensor 1 on the pressure side or sensor 3, those two values averaged together was too far outside of our threshold. I think it's plus like 10%, if you will. And then a message was sent back on the corrective action topic to go ahead and stop that production site. And so to dive into that a little bit further, let's go ahead and take a look at the topics we have. And so with that being the case, when a corrective action is sent out to stop a site, it is sent on the correction.outgoing topic. And so, interesting. Nonetheless. So I think with this being inside of Kubernetes, one of the things that's probably very valuable to be able to do is to be able to go ahead and take a look at the logs of the applications themselves. So if we get back in here, we've got the pods. So we have one corrective action producer pod. And so with that being the case, let's go ahead and spin up a new terminal here. Fix the typos. So with that being the case, we can go ahead and tail the logs off of the corrective action producer. And this is going to live, this does live in the applications namespace. So here we can see the logs from the actual application itself, sending out stop messages for site 36. We don't have exactly one semantics in place here. The really important thing here is that we send a stop message. So we never decided to go to exactly one semantics around a stop message because 1 is as good as 6 in this case. And so kind of digging back into the dashboard here around operations, go ahead and send a start all. We start producing messages. Site number 20 was outside of threshold. And so somewhere in these logs you can see that we sent a corrective action. So yeah, so up here we were stopping 20 and 25 roughly at the same time. So with all that being said, we've gone through the deployment of the stream applications. The next step is to go ahead and destroy the resources. If anyone, I don't think anyone's been following along in the room. You definitely will want to destroy the resources if you are on the live stream, as to not incur a bill, obviously. And I think with all that being said, I am out of material. Are there questions in the room? Would you like to dive into the Scala code to see how to actually interact with Kafka topics? I think we have about 30 more minutes. And this is basically your time. What's valuable to you all? Dive into the code? Yeah, sure. Cool.
Can you point to the diagram what that code actually says?
Yeah, sure, absolutely.
Have an idea.
Yeah. So in the diagram, the repo for the actual stream processing code, we are working on templatizing it. It's not currently open at this point, but in the next week or so, I think we're going to do that. Yeah. So in terms of the code that we have written that I'm more than happy to show you, there's 3 places that we wrote code. One is to synthesize the generation of sensor reading. And that's pretty simple. We can go ahead and jump into that pretty quickly. Actually, I'm just going to do this in Sublime because I feel like it won't take as long to examine the code base. So within the producer, as I said, this is all written in Scala. We'll dive down deep into the namespace. Cool. So it all starts at a main, if you will. And so our streaming producer comes in here on the main. It gets a start and end ID for the sites that it should produce for. It goes ahead and jumps into the config. I think this is probably worth pointing out pretty quickly. We have a case class in Scala that has the number of temperature sensors, number of pressure sensors to synthesize the production for, the min and max, and the target. And so the target is how we derive when anomalies have occurred. And we do that for both temperature and pressure. So at that point, jumping back over to the main class within Scala, we will go out and create, if it does not exist, the topics that we need. Since we are producing to a temperature and a pressure topic, we'll want to create that. Additionally, we have a correction topic, which is how we go ahead and shut down the synthesized sites. And so we create that in case we get a message to go ahead and tell us to stop producing for a given site. So in parallel, for each of the site producers, we'll go ahead and start sending messages. That occurs in one thread. And then we'll go ahead and subscribe to the corrective action topic. And at this point, we basically loop. And if we get a corrective action using the poll method, we go ahead and filter that down to the sites that we care about, i.e. the start and end sites for this process. These are the sites that we care about. And so we'll go ahead and do that. And for the relevant corrective actions, we'll go ahead and find the site, and we will go ahead and stop or start the site depending on the message that we got. And obviously, go ahead and log it out so we know what's going on in the human world. So with that being said, I think this is probably the next place to go in terms of creating the sensor config. This gets fed into the sensor config here. And then finally, the create topic method, we can take a quick dive into that. We have an admin client which interacts with the metadata of the Kafka cluster, and we'll go ahead and create a topic. And if we get an exception, given this is kind of prototype code, we just kind of drop it on the floor because the topic already exists. So with that being the case, let's go ahead and dive next into the sensor processor component of the proof of concept architecture. And so that is our aggregator. So I'm going to dive down into the namespace. And let's take a look at that code. Yeah, so it's a little loud behind me. I'm going to try to synthesize the question. The question was, can we run this outside of an EKS cluster? Does it have to be in Kubernetes, or can we run it elsewhere? Yeah, so these are just Java. These run inside of a JVM. So we've ran them inside of something like Cloud Foundry, which basically just stands up a Java container, if you will. I use quotes there on purpose. You could deploy them to a VM. You can deploy them into Kubernetes as well. You could probably easily modify this to push it into a service mesh product as well. It's really, this can run anywhere where Java can run. For simplicity, it was easier for us just to push it all up into the same K8s cluster. So digging into the sensor reading aggregator, we'll see a fairly similar we'll see a similar pattern here. We go ahead and create the topics that we're going to use. So this actually gets into the KStream library, and Kafka Stream is an encapsulation on top of raw producers and consumers that I think got added into Apache 0.10. So it's definitely adopted within the full distributable of Apache Kafka. Confluent created it, if I'm not mistaken, and it's gotten wide adoption. It deals with, I would look into K-streams for any kind of stream processing that you have to write. I think one of the things that really kind of set us free as a development team was it handles dealing with multiple partitions. You can have one partition or 50 partitions or 200 partitions, and the KStreams library will go ahead and deal with that. If you start kind of like quote unquote hand rolling your own consumers, you have to have knowledge of the partitions and build this logic into your custom code to be able to deal with all of the different partitions. So we got into this because we wanted to get multi-partition, and it allows for some pretty nice encapsulations. And so we are going to go ahead and window the sensor readings by both site and sensor. And so that being the case, we'll take the sensor reading topic and go ahead and group it by, let's see here. So we'll have to dig into this. Site and sensor reading. Not working out. So we have a grouping construct called site and sensor reading, or the mapper. And so at that point, let's go ahead and find that. So at this point, it's going to go ahead and group by. In Scala, we have the concept of an object. Within KStreams, the library, we have a key value mapper, which is going to take a key and value and modify it. And so at this point, we are just making the site a string. And so at that point, we have modified the values within the stream. And so at that point, we're also we're grouping it by that sensor ID, or by that ID, the site ID, and then we're going to go ahead and window it. And so when we get into windowing, and this is to your question earlier, is that, what's that look like? What's the configuration there? We are just pulling out a millisecond, an integer that represents the number of milliseconds that we want to group by. And so we're going ahead and creating a time window based on that duration. And so that's where you'd modify that. And so the kind of just there to kind of dive into sorry to hop around so much. Oh, why does the application create the topic? Is that the question? Oh, I never created a topic. We didn't code that out in the infrastructure. So when the application comes online, if the topic doesn't exist, it'll create it. And if it does exist, it just swallows the exception. So this makes our code responsible for creating the topic.
No, when you package that Docker image, and then you can say these are the instructions, right? When you bring up to Kubernetes, you can create the topic on the fly, right? Then like your code doesn't need to, because every time you execute, right, it goes and traces around.
Yeah.
You just configure the topic to your Docker image and customize and match it to the Kubernetes.
Yeah, I agree. So for the stream, the activity of like creating the topic on the fly from the code isn't really as efficient as it could be. We've certainly coded that within our infrastructure in certain cases where we go ahead and create it ahead of time. I think for this being demo code, we tried to make it as as tough as possible.
Some production code, right? Even like some of the
Yeah, oh, absolutely.
You don't need to block the threads like loading them.
Yeah, absolutely, absolutely.
I mean, like, totally demo code is fine.
Yep.
But it's production, like,
Yeah, so I would say that there's a concept within a Kafka cluster for auto topic creation, and I have seen that enabled for lower environments, but we do not enable that for production environments. You cannot just go and create your own topic on a production Kafka cluster. I completely agree. Yeah, this being demo code, we took the low road, if you will. Oh, sorry, what's the question? Sorry, I can't hear you. There's a little noise behind. Oh yeah, absolutely. Yeah, we can definitely share the slides out for sure. We'll send that out in an email to everyone who signed up for the meetup. Yeah, absolutely. Yeah, I totally agree. In a production environment, don't let topics just get created because you're gonna have a mess. I think there's probably a corollary there as well. Like with your lower environments, you probably need to go and wipe out old topics that have been created, maybe superficiously, if you will. So yeah, completely agree. Yeah, I've seen both approaches where you let topics kind of come into existence as the consumers and producers want them, but once you get into production, definitely lock that down. And then also, you've got another conversation around the schema registry there, because you can have different levels of evolution of the schemas of the topics. In production, you really want to control that and know when a new message shape is going to show up. So I would definitely recommend locking that down. Yeah. Yep, absolutely. Yeah, that would be a best practice. Yeah, completely agree. Yeah, good point. Yeah, thank you. Yeah, have a good night. And so, to dive back into the aggregator, which is by far the most complicated of our custom code, we'll go ahead and aggregate the by the site ID, and then we will reduce. And so this reduction is where we really start to see the average of the sensor readings over a given time window come into play. And so let me see here. Let me find ag reducer. This is not my normal ID, so it's a little, I'm going to kind of be fumbling around. Sensor reading aggregator. Let's go find this. Okay, so we're grouping and then we're aggregating across here. And so this is where we go ahead and then take the readings and go ahead and average them across the time window. And so then we get into the Anomaly Mapper, and there's quite a bit of logic in here. And so at this point we have the group temperatures and the group pressures across the site ID and the sensor ID. And then we go ahead and pull out the temps that are above target. This is pretty darn Scala-esque, so I apologize for the syntax, sort of, not sort of. I do like the language quite a bit. So at this point, we are going to take the average across the readings, and then we're going to take that across the target and determine how far from the target they are. And we do that both for temperatures, and we do that for pressures. And then at that point, we go ahead and send out the temperatures and pressures that are above the target, and we tell you on a ratio how far above the target they are. So Scala is a pretty interesting language. If this looks pretty, so we're dealing with the tuple kind of syntax here. If it looks like a lot, Scala is a lot. It's powerful, gives you a shorthand way to deal with problems of this nature. but it does look kind of intimidating at first, so apologies for that if that is the case. And so at this point, we are now sending out the pressures and temperatures related to the target and how far above them they are. So how far out of whack are the readings? And so with that being the case, those will then flow into the anomaly topic. And so at this point, we've got the readings on a topic. We've determined which sites and sensors are outside of the expected thresholds, and then we've put them onto an anomaly topic. So with that being the case, the final piece of the code here, and we'll dig way deep into the namespace again. The corrective action producer is what takes the anomalies and determines if they are too far outside of the thresholds, and will tell a particular production site to stop or stop. So going back to the diagram, let's take a quick dive into the action coordinator. And so at this point, we've sent the anomalies out on this anomaly topic, and then the final concern within the system is to determine if the anomalies are too far out of whack. And so with that being the case, let's dive into the main Scala here. So again, we go ahead and create our topics. To the point earlier, maybe that's not a best practice in production. And so at this point, we go ahead and grab the corrective actions and send a stop message. So with that being the case, all of this starts with the stream builder.stream, and it pulls off the anomaly topic. Inside of our configuration, we have a anomaly variance threshold, and if the variance that we see coming across that anomaly topic is greater than or equal to the anomaly threshold, then we have qualified anomalies. And so with that being the case, we go ahead and reduce this down, trying to reduce the number of messages we send across the topic. And then we'll go ahead and send the messages through the correction topic, which, if you recall from the producer side of the equation, this is listening to the corrective action topic, and if the corrective action topic tells a given Java process to stop, we'll go ahead and send a stop message into that the part of the process that is synthesizing the manufacturing site. So I realize 20 minutes to dive into a code base is probably really just going to create more confusion than answers. But we are starting to come up on our time limit here. I think we have another 15 minutes to get into Q&A, etc. Questions?
Can you compare this to Kinesis, and can you also talk about like how much development time are you maintaining? You know, a lot of the streaming world is moving to serverless.
Sure.
Can you compare that to Kinesis, basically?
Yeah, absolutely. So, I mean, it is a very similar, Kafka is a similar paradigm to Kinesis, and that you're dealing with data streaming. I think if you start to get into a really large volume of messages, the cost of Kinesis starts to really kind of balloon. It's the whole, serverless versus IaaS problem over and over and over and over. And so you have a similar technology there. So you get into, with Kinesis Stream Analytics, which is where like K-streams or K-SQL might come into play, you've got a different language. But once you start to get to a volume of messages that I feel like is substantial.
My other point is how much development time is the person that built it going to be trade off?
Yeah.
You know, when you're sending a billion messages, whatever a day, like where does it start to trade off in terms of, you know, going serverless or keeping this development up?
Yeah, that's a good question. The payoffs of the custom development, you know, it pays off at scale. So once the volume of messages increases with the kind of the paradigms and constructs around Kafka, it scales very well. And so there's not really a point in which you start to, I don't know, see better performance unless you have hand-rolled your consumers, as I like to say, in which you're paying attention to only a single partition. So as you start to get to a large volume of messaging within Kafka, I think you really want to go to a library such as Kafka Streams or something of that nature, where it's going to deal with detecting and kind of fielding the partitions as they grow. Yeah.
So with talking about operational overhead, can you use Fargate with your Kubernetes cluster so you don't have to manage all your underlying instances and stuff, or would that be affected because of Kafka and the replications and having your data and your different nodes and stuff? Because then if I was with Fargate, it'd be more ephemeral. So would I be able to use some of that Kafka with Fargate?
Yeah.
If I wanted to go serverless with my Kubernetes cluster?
Yeah, I think our example probably not, but yeah, you can definitely deploy Kafka to a serverless container service such as Fargate. So yeah, you could definitely go that route.
So that'd be kind of meeting halfway between less operations and still using Kafka to manage your scale and application.
Yeah, I think at that point, when you're talking about getting into something like Fargate, serverless containers, etc., you get the benefits of the Kafka cluster at scale, but you don't have to really you don't have to pay as much attention to the kind of the ins and outs of the K8s cluster, because Fargate's going to do that for you. Yeah, so I think you can definitely do that. And it takes away from some of the management overhead. Like, for example, this solution introduces an EKS cluster. Someone has to know what to do with an EKS cluster in a production environment. Once you get into Fargate, you're kind of offloading that management to the cloud provider, AWS in this case, and you can really start to just hone in on the data streaming service, Kafka itself. Yeah.
How easy would be to adapt this architecture, let's say, to process stock prices?
Oh, yeah. So I think that's a pretty common use case. So the question that I have is, where are the stock price events coming from? So you're going to have something that's basically pulling the stock prices from some data source. At that point, you could very easily take the stock prices over a window, aggregate them, and say, is it going north or south? And if it's going north or south, is it going north or south, the price on average that is, and a magnitude that requires some sort of action to occur. So I think it's probably a use case that really makes sense here that could be adapted to pretty quickly. Because at that point you're really talking about, with a set of stock prices, what are the anomalies? If a stock starts to, over the course of 30 seconds go up more than 10%, just throwing numbers out there, that's a pretty wild growth in the price over a very short window of time. So this could be adapted to deal with something like stock prices pretty easily. I think the thing I would really be concerned about are, how do you define the thresholds of what's an anomaly within the stock market? That's hard to me. Yeah.
No, that's the key. You should be able to change the min, max, and targets.
Mm-hmm.
So that as you see something going up, then you may change the area that you're looking at.
Yeah.
So that the corrective action is
buy or sell. Yeah,
buy or
absolutely.
sell,
Yeah.
can go with the market, so to speak.
Yeah. So that's interesting. Like as of, I guess in this example, we're just pulling the min and the max and the threshold out of a config that's basically set on the environment at the time of deployment. So at that point, I think you're talking about something that maybe could be called like dynamic configuration.
Yeah.
And so you would have to be able to, that would be a design point within the application is, you know, like once something jumps 10%, is its next threshold 5% or is it 50% or like what is that? So I think that's certainly not logic that we have baked into our application.
Asking for a flexible these days.
Yeah.
I mean, ideally, if you equate site IDs to
Stock symbols.
stock symbols,
Yep.
then you should be able to configure each site.
Yeah. Yeah, oh, absolutely. I think that's definitely the case. So I think the kind of the core of this solution would be adaptable to that, but like I said earlier, like what you consider an anomaly and what the threshold is as time changes would be, I think that's the really interesting part of that problem. Yeah, that's a good question.
Thank you.
Yeah. Yeah, I feel like you could even maybe take that anomaly topic and use that to adjust your thresholds. I think that would probably be where you go. And so once an anomaly occurs, you also are consuming off that anomaly topic and you're figuring out from like, just say like the original, like if something jumps 10%, that's big, right? And so then an anomaly goes out and says something has jumped like 12%, for example. Then you start to use those anomalies to adjust your next anomaly target. I think I would probably try to get someone in finance involved with this problem, but you can certainly use the constructs of the technology to kind of scale your thresholds. That'd be really interesting.
Use Kafka in an environment that is not event driven necessarily. And I want to make a comparison. Microservices use events,
Mm-hmm.
subscribe to those events and react. Would you use Kafka in an imperative way, like write something like that to this to synchronize data?
Okay, so help me like maybe like synthesize the question. So
Again, we do customer stuff, so you have two systems that integrate each other. They don't know anything about them.
yes.
Right? You get data conflicts, stuff that you have to resolve. How would you use Kafka?
Oh, okay. So to resolve data conflicts from disparate data sources, how does Kafka come into play there? Oh, yeah. Okay, yeah. So what we did in that case, there's a few different products that can help you cleanse and match data. Informatica is one. There's a product called Trillium that also does something similar to Informatica. You're basically going to have to identify records that are the same or from like the same origin. So like you get address from one place and you get last purchase from another place. And so you can use something like Kafka to say like something has changed and then go out based on that event of something has changed with the customer and start to pull data from the various disparate data sources and build this kind of golden record is a term that shows up in the industry quite a bit. So that's one technique. But, let's say that a customer has acquired another customer. Like at that point, you have to figure out what is the right address. And so at that point, you have to do something along the lines of ranking the data sources and figuring out what's the authoritative data source. And that's the tricky part. And at that point, you have to sit down with your data stewards and figure out from your aggregate data sources, what it is that is the most authoritative of those, and when you start to assemble those, pick from the correct disparate data source. So it's kind of tricky. People have to know the data sources really well. Like you need people within the business that actually understand the differences within the various systems, if that makes sense. Okay, cool. Yeah.
Certainly a question for you. Customer is a big topic, so what do you have in mind?
So yes, in microservices, custom means different things for different domains. What you have a website, right? It has a list of customers. You have an integration with SAP or with CRM, whatever.
Mm-hmm.
You need to synchronize that data. Not right came from the website, an update came from your SAP system or CRM.
Yeah.
Well,
It's
it's
very just
okay. I have been around that problem at Dell, and when you have consumers coming to a website, you don't know who they are. All you have is a session ID, and then as you start asking or finding out stuff, then you have to correlate it with something you know, until you identify, oh, this person is, this connection here is this person over there.
which is the solution that you're saying.
Yeah, it does require a pretty in-depth knowledge of the various data sources and knowing which one is authoritative.
Now, the problem that you mentioned about disparate values, that's just a master data management that
Yep.
you mentioned. Is Informatica we would apply and say, let's say sex comes as 1, 2, 3, 4, 5, whatever, from this source, but it comes from MF, blah, 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 from this other source. Then you have to
Yeah, you have to join the data.
put them in the same domain, so I'm not talking about.
Yeah, it has to be the same domain, right?
Mm-hmm. Yeah, absolutely. Yeah, it's definitely not a simple problem.
I think it's still nice to use Kafka for that kind of stuff because all those events that happen, they just get written down. You can just think of it as like written down as permanent log of all the events on both different systems.
You can replay the
You can replay them,
Yep.
and like they all have timestamps and they have a fixed order. And really like using Kafka streams, you can like do the joins or whatever with respect to the timestamps so that everything kind of happens the right way. You can imagine like do a change, from one system, and then you like totally change the customer like ID or whatever on the other system. You need those to happen in the right order.
Yep. Yeah, as you change your business logic to determine what should compose a customer, say you acquire another company that has a source that is now the new authority on address, replaying it is incredibly powerful. What is it? Event, my brain is fried. Event sourcing model really has a ton of flexibility. You pay for the storage, but it's honestly not that much in a modern world. So why not just keep the events around?
That is a real life problem. Dell.com, we have that issue.
Yeah.
Because you log on and let's say you're configuring stuff, and then you can save the configurations of Dell for 15 days. And then you can give it any email address, you can give it any username. So how do you know that these configurations is the same user that created these configurations? Right. So
Yeah.
it is a real
Yeah, this is definitely a real problem. Okay.
That's not even talking about spiders, because spiders can change IDs.
Oh yeah. Yeah, we ended up deriving our own ID for what a customer entity is, and not really trusting the IDs out of the source system too awfully much. Because yeah, once the IDs start changing, if that is what you're keying on, your whole system is broken.
Right.
It's a terrible mess. We made our own IDs for this particular problem.
So that was the message ID that you were saying, or that's something
Yeah,
else?
we would like once we combined all of the data, the ID of the message that we sent down to the downstream consumers was this derived ID. So we had to go figure out, is this part of this ID that we already know about, or is this a new entity? And it was pretty interesting. It's a big problem. There's a lot of things to think about there.
I think you could, to answer his original question, I think you could use it
Thank you.
against a data lake. Let's say you have compiled a lot of stuff on a data lake, and now you're trying to simulate what happened, or analyze what happened over
Mhm.
time.
Yep.
So then you could
If you have the whole log, yes, you can do that.
Yeah, absolutely.
If you have a lost log that comes back up, it could override the data.
Yeah, I think there's a concept called compaction within a Kafka topic, to where if the key is the same, it just keeps the most recent data. So you definitely get into that scenario where same data comes back up, new value, and all of a sudden that's the most recent copy of the truth, and that is the message. If you were to go query the state store, that you would get in a compacted topic, if I'm not mistaken. Yeah.
Yeah, that's how, New York Times can keep every article they've ever written in Kafka.
Yeah.
So just think about like in your database, you've got every record you've put in there, right? Like
Mhm.
it's all just there in the database. Every little like insert, transaction isn't there anymore because those logs get
Yep.
but like the final state of it is still sitting there. The same thing happens with the Kafka topic.
Oh yeah, the most recent version of the truth is right there at the ready in the state store. Yeah. All right. Well, I feel like we're a little over on time.
Thank you.
Any final questions, or shall we just go ahead and wrap it up?
Thank you.
All right. Thank you all for coming out. This has been fun. All right. Yeah.